Okay, well, before lunch, talked about river-dominated deltas and pointed out that they're complex, that they typically form where you have kind of a sheltered shoreline, so the river brings in sediment, and that sediment is just kind of dumped there, deposited, and as more sediment is deposited, the whole delta system migrates in a seaward direction or progrades in a seaward direction. Now we'll look at wave-dominated deltas, and they're quite different. Actually, they make better reservoirs than the river-dominated deltas. And a good modern example of that is the Nile Delta, Egypt. And so here's an outline, an air satellite picture of the Nile Delta. It's a delta-shaped body, as you can see from this diagram. And it's got two main rivers that are emptying into or supplying sediment to the mouth of the delta. One of those rivers is called the Damietta River, this one right here. And on the air photo, you can barely see it right down, comes across like that. And the other river is called, I've got it upside down here, it's called the Rosetta branch of the Nile River, and you can see that one right over there. So this little active delta part is right here, and the active delta part down is this one down here. And those are actively, those shorelines there are actively accumulating sediment. The rest of the area is not so much, and that's why you see all that green vegetation there. So the key characteristics of a wave-dominated delta like this one is that the river will bring down sediment. Let's say this branch of the river will bring sediment down to the mouth of the river, and you've got waves that kind of are in this sort of an orientation, almost parallel to the river, or almost parallel to the shoreline. And so what happens is when you bring the sand down here in that river, it gets dispersed along the shoreline. The wave action tends to move it in a direction, and so over time you get a nice sand body built up here of river sediment that has been reworked by waves, and that reworking gives you good sorting and grain size, and so you get good porosity and permeability, and one of the key factors is you have very good connectivity. Much better connectivity than you did in the river-dominated delta. So here's a couple of pictures that illustrate that. Here's a shoreline there, and you've got a river that's bringing sediment down to the shoreline. If this were a river-dominated delta, that sediment would be just piling up at the mouth of the river, but it isn't. It's a wave-dominated delta, and you've got some waves that kind of have this sort of an orientation to them. And so the end result is that when this sand is deposited, it doesn't stay there very long, but it moves by the action of the waves, it moves parallel to the shoreline. Here's another example down here, where you see here's your river, and what you see here, these series of lines here, are old shorelines. The oldest shoreline is right there. Then you've got another one that's a little younger, and another one that's a little bit younger. So with time, what is happening is you're prograding this delta, but in a direction more or less parallel to the shoreline or perpendicular to the river. Here's the same thing. Here's the river here. This diagram. It deposits the sand, and then the sand gets reworked into these old shorelines. So you have an old shoreline there, another one there, getting younger and younger. And so you have a series of prograding shorelines in that direction. So in that way, that's how the sand builds up. It's reworked sand, unlike the river-dominated delta. And us geologists, if we're looking at core, for example, there are certain features that you can see if you're looking at core that tell you you've got a wave-dominated delta. Now, I won't go into what those features are. There's a whole bunch of these that geologists know about, and they are indicators of wave action that rework sediment. Because the shoreline is prograding seaward with time, you get this coarsening upward pattern. And if you had a well log, you'd see the same thing. You'd see something like this on a gamma ray log. Okay, something like that. Where your best sand is your up here near the top of the delta sequence. So that's what you get vertically. The best reservoir is going to be at the top. Grain size is coarser. Remember the permeability relation to grain size. And so your permeability is going to increase upward. And that's what's illustrated in this diagram. Here's a gamma ray log. Permeability is right here, very low near the bottom, and then it gets much better near the top of that sand body. Porosity changes a little bit, but not so much. So that's a characteristic feature vertically of a wave-dominated delta. Now, laterally, because you're reworking that sand when it hits the shoreline, that sand tends to get spread out, and so you get very nice, good lateral continuity of your sand. So this sand right up here, you can predict is going to be very laterally continuous, good permeability, and so it's going to be, in this wave-dominated delta system, it will be your best reservoir will be up here, both in terms of lateral continuity as well as the increase in permeability upward.
Professor,
yeah.
These are wave-dominated deltas.
This, yeah. Yeah, these are wave-dominated deltas. That's what they look like, yeah. Now here's one in Greece. I had a chance to go to Greece once, and this is about 1,000 feet or so, this cliff, and it's all sand. There's maybe 1 or 2% clay at all, if even that. And it's an example of a wave-dominated delta, where you get all this, the upper part of a wave-dominated delta. In other words, we're looking at this upper part here and there. So you've got about 1,000 feet now of all sand. Now, if this were in the subsurface, it could well be a very good reservoir. But look at all that sand. I mean, that's a huge pile of sand, 1,000 feet thick, and no telling how many miles wide it is, but probably quite a few. So that's an example of a wave-dominated delta, and it's a much better reservoir than the river-dominated delta. Okay, let's look at the third type, and this is a tide-dominated delta. That's this one here. And a type example of that is the Nile Delta, this one's off New Guinea, Gulf of Papua. And here's the river, the river that's supplying the sediment. You've got this narrowing bay, and the situation is something like this. So you've got this bay that's becoming narrower. So in areas where you have strong tidal currents, when you've got the incoming tide, for example, it's going to start to build up as you get more and more into this constriction area here. And then the outgoing tide will do the same thing. It'll push the sediment, the sand out. So the end result is you get a very well sorted sand body, but the sands are not connected, but they are parallel to the orientation of the river. So here's the river coming in. This is actually the river here, a couple of branches. And down here in very shallow marine water, these yellow linear features, those are your tidal, what we call tidal sandbars. Tidal sandbars. And that's your reservoir. That would be a reservoir in the subsurface. Now, these are isolated. These sand bodies tend to be isolated. And in between them, let me back up. The sand bodies tend to be isolated, and they're going to be mounded. They're kind of a mounded feature, elongate, mounded feature. So in between any two of these sand bodies, you're going to have a low area, okay, what you're called here tidal channel deeps, okay? In other words, a deeper area. Well, when the tides come in and out, they rework the sand in the orientation of the tidal currents, but the area in between the tidal sands being deeper, lower energy, so you get mud tending to accumulate in between the sand ridges, the tidal sand ridges or sandbars. So if you look at a view something like this, you can get a better picture of that perhaps. The yellow is sand. These are the sand ridges. See that orientation that is parallel to the orientation of the river. The river is bringing the sand down, but then it's dispersed back and forth by the action of the tides. If I had a steadier hand, I could draw better arrows. Can't draw very good arrows. That's supposed to be an arrow, meaning tides coming in and out that rework the sand. And the brown areas here are the areas between the sand ridges, and those are going to be filled with mud. So, because they're somewhat deeper water, slightly deeper water. So, through a stratigraphic interval of a tide-dominated delta, it's going to look something like this in vertical dimension. This cross-section here is taken right about there. So what you get is you get nice cross-section of the sandbars. Sandbar, sandbar, bunch of them together. And in between a lot of those sandbars is where you'll get your mud or your shale. And that's what the brown areas are. So it's a form of compartmentalization that you don't get in river-dominated deltas, nor do you get in wave-dominated deltas. It's exclusive to these tide-dominated deltas, where they're oriented, the long axis is oriented parallel to the river, and each one of these ridges is separated by a shale. So you end up, this is your vertical stratigraphy. So you don't really, if you can help it, you don't really want to drill a vertical well. For example, if you drill the vertical well here, you'd get a little bit of sand, but you'd also get a lot of that shale. If you drill a well here, you're going to get a lot of sand and just a little bit of the shale. But if you drill a well here, you get hardly any sand. It's almost all shale. And so in this environment, you're actually better off if you can drill a horizontal well, so that you come down in through here, stay in the zone, and out like that. That way you penetrate, you go across these shale breaks here, and you penetrate the shale breaks and go past them or through them and get into the next sand. So if you drill a horizontal well all the way across, you're going to penetrate several sands and maybe just a few little shales. Just like the wave-dominated deltas and also the river-dominated deltas, the tide-dominated deltas have various unique geological characteristics that allow you to determine that you've got, in your core, for example, that you've got a tidal sand ridge deposit. Because the deltas all prograde, you're getting a cleaning upward pattern on your gamma array log or your core, because you're depositing older, muddier sediment, and then you're depositing sand on top of it as you get this progradation. Okay, let's look at a field, a reservoir. Here's an example from Venezuela, Lagunitas field in the Maracaibo Basin. And this is a isopack of the net sand thickness here of one of the reservoir intervals called interval A. And yellow is where you have 60 to 70% sand. Black is where you have greater than 70% sand, so very high net sand. And where it's white, you have less than 60 feet of sand. So you see these nice linear sand ridges that are all aligned. In this case, the tidal currents would have been something like this when this was deposited. They would have been going back and forth something like that and building up the sand into these ridges. Here's an interval B in the same area, and it's even sandier. The black area again is more than 70% sand, and the yellow area is 60 to 70% sand. So you see a lot of nice, very sandy ridges like that. So once again, if you drill a horizontal well, now looking at it in plan view, well, let's do it this way. So looking at this in plan view, you might drill a horizontal well that kind of goes through all these sands. It might look in cross-sectional view something like this. And then you go up to the next interval. Again, if you drill a horizontal, it's going to be even sandier. And so you drill something like that, and you stay in the sand. So by drilling the horizontal wells rather than the vertical well, you increase your reserves. Now, it costs more money to drill a horizontal well, but you can make that up usually with the additional reserves. A well in, say a vertical well right here, wouldn't show you very much. There's not much sand, so that's probably going to be a dry hole. Drill a well here, very sandy, that's a good well. The same thing if you drill a horizontal that goes through, you see a lot of good connectivity of the sand body. So at any rate, the bottom line here is that you really need to know the delta type to understand how to produce it from a delta. If you're just saying you're working on a delta, that doesn't cut it. You got to know what type of delta because the geometry of the sand bodies are different. So here's your river-dominated deltas with the distributary mouth bars spaced widely. Here's a tidal dominant delta where your sand bodies are parallel to the orientation of your river. And then a wave-dominated delta where your sands are perpendicular to the river because they're all deposited in different ways. So you need to know this if you're going to set up your drilling program. If anybody ever asks you what type of delta you're working on, that's a trap. They're going to trap you into saying, I'm just working on a delta. I don't care what type it is. Say, well, you better care what type it is if you're going to maximize your performance. Okay, well, I've talked about a little bit about progradation and regression, and I want to talk about that a little bit more, particularly what you see on seismic. So here we have examples of progradation. So let's say we have a package of sand where here's the bottom of it, and if we trace all of these downlapping seismic reflectors, we get a pattern of downlap. And that's what progradation is. You're prograding your sediment body in a seaward direction. So here's land, here's sea. Now, sometimes you can get what we would call an aggradational delta with aggradational downlapping reflectors, where you get this break and slope more or less at the same location. That's due just to vertical aggradation, where you just keep depositing sand on sand on sand without any lateral movement. You can have retrogradation or transgression. They're pretty rare for deltas, except for these, what I haven't talked about yet, so shelf margin deltas, which tend to form during transgression, and actually during low stand as well. And they're ones that kind of backstep the landward direction. And then you've got an oversteepened, which you can see, here's the shelf edge, and you can see that shelf edge migrating from left to right with geological time. Well, why is it sometimes you get one type and other times you get another? Because this is going to be important as to determining where the distribution of the sand is going to be from your seismic information. You would like to know that. Where can I predict? Where in this mess here can I predict that there's going to be sand? Okay. Well, there's such a thing as what's called a shelf edge delta. Remember, I said before lunch that most deltas form during a high stand of sea level, when you've got a lot of space between the sea surface and the sea floor, so that sediment can prograde across that space. Well, sometimes that's not the case. It is possible during a drop in sea level to have what we call a low stand delta. They don't make as good a reservoirs usually as a high stand delta, but you do have some reservoirs, like off in Indonesia, there's lots of low stand deltas, for example, that are very good reservoirs. And how they form is kind of illustrated in this old diagram, where you have a river coming down during a falling stage of sea level. So let's say we have a river here and our shoreline there, and we're getting low stand time. So what's happening is that the shoreline is migrating seaward with time. So this might be the shoreline at that particular instant in time. With time, because you've got this regression and progradation, your shoreline is going to, after a while, your shoreline will be back there. And after more time, here's one shoreline. Older shoreline back here. And with time, we'll continue to prograde, and essentially what you're doing when you're prograding is you're pushing the shoreline in a seaward direction. Your sedimentation rate, to get that sort of a pushing of the shoreline seaward, that sedimentation rate has to be very high, so that you constantly are filling up that space between the sea surface and the sea floor. You fill it up with sediment, so that pushes the shoreline seaward. You deposit more sediment and it keeps on going. So we'll just put one more shoreline in here. Put that in as another shoreline. So during progradation, you have pushed the shoreline seaward. Another word for this would be regression. And if sea level continues to fall, you create an unstable slope up here. And so you get sediment being moved from upslope from the shelf edge down across the shelf edge into deeper water environment. And eventually it can go all the way down to that deep water environment. And you accumulate shelf, what we call shelf edge deltas, because they're occurring at the shelf edge. And very importantly, they're occurring during progradation, when you're pushing the shoreline in a seaward direction. Well, let's look at an example. This is the Gulf of Mexico, the U.S. side of the Gulf of Mexico. The city of New Orleans is somewhere down in here. This is the shelf edge. There's a submarine canyon here. And if sea level now were prograding in this area, say moving so that the shoreline was moving in a seaward direction, you start getting these shelf margin deltas slumping over the shelf edge. Okay, so you get a whole bunch of those. Now, if sea level continues to drop, let's say down to a position down here, same process is going to happen. You're going to get shelf edge deltas forming down there. Like that. These can be reservoirs again. They tend to be a little bit muddier than your big deltas, where you get more sand, but they do make reservoirs. And the reservoirs, this would be a hypothetical cross-section through a set of this progradational depositional model, where you've got the sea floor. Draw the sea floor in a different color. Okay, here's the modern day sea floor. You've got the shelf where the deltas form, the high stand deltas, or the deltas. You've got the slope and you've got the basin. And this feature, this downlap feature that I've been showing, is called a slope mudstone. There you go. Your sand is going to be up here, and the sand is prograding over the shale, and that's why you get a pattern of a cleaning upward. Why you get that log pattern of a cleaning upward sequence going from shale to sand. And you've got these little features that represent intervals of time where you really don't get much sedimentation at all. And we call those clinoforms. They're clinoforms, C-L-I-N-O-T-H-E-M, clinothem. Here's a real picture of one, or a set of them, in rocks. This is pretty large scale. It doesn't look like it here, but it is, where you can subdivide your progradational delta into three parts. One part we call the bottom set of beds, and they would be beds that form first on the sea floor. Then you have your, what we call the foreset beds, that are actually doing the progradation in this direction. And you've got the topset beds up here that are forming like about in this position there. Well, where's the sand going to be? Typically, in this sort of a situation, the sand is going to be in two places. The sand is going to be up in the top set beds, and it's going to be in the bottom set beds. So back to our cartoon. Where you've got your bottom set beds, which are flat lying, and they're going to tend to be sandy. Up at the top is where you get your delta sands, and they're going to tend to be sandy as well. Everything in between is going to be dominantly shale. So that would be a profile through a slope where you had a fall in sea level, such that you were able to build out one of these shelf edge deltas. So do we see these on seismic? Well, we do. Here's a good example from the north slope of Alaska. And you can see up here, the bottom set beds of the delta are the flat-lying ones down here. Well, I want that one. I don't want that one either. Trouble with my colors here. The four-set beds are going to be these that are downlapping. And then the top set beds are going to be where your sand is. Make that yellow, sand. Can't draw. Well, your top set beds are going to be up in here where they're flat lying again. So what I've tried to show you there is something like this, where you have bottom set beds down here, four set beds here, and then top set beds there. The top set beds are going to be the coarsest grain. They're going to have the best reservoir quality, and that would be in one of these low stand deltas, that would be your target interval to drill your well. So just some pictures of different styles of these shelf margin, these low stand shelf margin deltas. Okay, let's look at what used to be the third largest oil field in North America. It's not anymore, but it used to be, and it's called the Kapparik River Unit on the north slope of Alaska. And Prudhoe Bay Unit, the one I talked about yesterday, is right next door to it. So we've got the Prudhoe Bay Unit, and then to the west, we've got the Kapparik River Unit. Well, here's a well drawn through the Kapparik River Unit. Okay, one of the wells in this file. And what you see is a series of sands. a sand here, another sand here, and another sand there, another sand there. We can name, or this is a very old field as well, and the geologists that worked on it named it, gave these different units names, like this sand here was called C4 and C3. This sand here was called C1, and they just combined that into a C unit. This shaly beds, they called unit B, and then the sandy beds down here, which are not near as sandy as the beds up here, call that unit A, with a number of subunits, 1, 2, 3, and so on. Well, what does this look like? It should look like something like this, where you've got sands here, your bottom set beds, then you've got your four set beds which are steeply dipping, so they're susceptible to this instability and sediment moving down the slope. And then you've got but a lot of mud in this environment. And then you've got your top set beds here, and they're going to be sandy as well. So if you were to drill a well through this now, drill a well, see, if we were to drill a well, we'll say drill a well right here, like that, and we run a gamma ray log in that well, what are we going to see? We're going to see sand, and then shale, and then sand again. Of those two sands are not going to be equal, though, equal reservoir quality or things like that. The upper sand is going to be a better sand than the lower sand. Okay, this lower sand was deposited in somewhat deeper water where you get some mud mixed in with the sand, so your porosity and permeability is relatively low. Whereas up here in these top set beds, they're deposited in a very shallow, high energy environment. So you're going to have good coarse grained sands. They're going to be well sorted, so they're going to have good permeability. So even though you've got two sands, they're different. And it's just like having two separate reservoirs separated by some shale. Lower one being the bottom set beds, four set beds, and then the top set beds. And that's what we see here in the Kaparic River field. Now, so these would be, this is a deltaic reservoir, the Kaparic River field. These would be your bottom set, your four sets shales, and your top set sands. And of those two sands, which would be the best sand? It would be the top set sand, would be a better reservoir quality, greater continuity, greater thickness probably, all those characteristics, much more so than the bottom set beds. Well, what I want to focus on is this lower unit, which we call Unit A. Now, notice, let me get rid of the colors here. Notice that Unit A, the character of the sand, is one of a cleaning upward progradational character, just like we saw before. Progradation, progradation. And this is only for one well. There's a lot of wells in the field. Now, this is an old field again, and for many years, it's interesting, I heard a story like this at lunchtime today. For many years, the geologists, when they drilled wells, like these wells here, they would see a sand body here, sand body there, sand body there, sand body, sand body, sand body there, and they'd call that one sand, okay, and they'd correlate it. Sand coming across. Well, at one time, some young geologist came in and said, I just finished graduate school not long ago, and I think you're wrong. Said that to the manager. Well, the manager said, look, son, I've been around for 40 years, and that's the correct correlation. The young guy was persistent. He says, no, I don't think so. You know anything about our modern thinking, our concepts of how we think now of geology that we didn't 30, 40 years ago? And finally was able to convince the manager that, okay, you try a different correlation and see if you can do any better. Why were they concerned? Because some of their wells were good wells and some were bad wells. And they couldn't understand why. They said, look, this is one sand body going across. Everything's connected. So all the wells ought to be good wells, but they weren't. And they had to drill these closely spaced wells for that reason, because there was no predictability that worked. And so the young geologist was allowed to try out some new methodology or new concepts. And the reason, yes, sir.
When you're going to study this kind of reservoirs, I don't know, maybe they take some course or they make pollution tests, because if we see the cartoon of the reservoirs, we can see that they are independent.
Well, you can see it because I drew it.
Yes, I know, but before.
Just imagine all you've got is the well that shows the sand here, the sand there, and the sand there, and the sand there, and the sand there. And it's up to you to figure out how to correlate. Okay? I drew the answer that I'm going to give you right now. But for a long time, for many years, one generation of geologists, they were saying, well, look, it's all the same. Okay, it's at the same stratigraphic depth, so it must be, those sands must be connected like that. Okay? This is an issue in the oil and gas industry. Maybe some of you have faced this issue. I call it kind of the generation gap or the technology gap. And it's always going to be with us forever in the oil industry. And what that is, and I'm not saying anything bad about anybody, I'm just saying the way it is that the people who are supervisors, managers, vice presidents now, they came up through a system where we had a certain amount of knowledge. Well, with time now, and as we do more, we improve our knowledge, we improve our concepts, and things like that. And so the newer generation comes in with all these new ideas, and sometimes they're met with resistance, sometimes they aren't. I remember a grad student of mine that when he went down, got out of school and went to work for a company, and he tried to bring in some of these newer concepts, and they almost fired him. They said, if you don't stop doing this and do it the way I did it for 30 years, you're out the door. So you run into that sometimes, and you just have to use a little finesse or technique to convince your manager to let you try the new techniques. And this is always the way it's going to be. Right now, all you guys are very computer literate. I'm not so computer literate. I'm almost illiterate when it comes to computing. The advantage I have, though, is that I know I've learned what a computer program can do, but I can't sit down and do it myself because I don't do enough of it. I'd forget. I do computing with Petrel, for example, for 2 days, and then I go away for a month and come back. I've forgotten everything. Whereas you guys can sit down and work Petrel, for example, and build a model, go away for a month, do something else, and when you come back, you can get right back at it again. So that's a generation gap. And now what's going to happen, you guys are at a certain point in technology, but in 20 years, the technology will have passed you by. There will be all new technologies. So you guys are going to be the managers saying, do it this way, because that's what Slatt said to do. Okay? So there's always going to be that generation gap, and it can be a real problem sometimes, hindering progress. So even though I can't sit down and, for example, play with Petrel, I know what Petrel does, so somebody can do it for me or for themselves, and I understand why they're using Petrel rather than the way I used to do it. We hang logs on the wall, paper copies with a piece of string. That would be your stratigraphic datum, and you'd hang your logs that way. That's the way I grew up in the field. Well, nobody does that anymore. You've got it all, your cross-section. You can make your cross-sections online with a computer program, make your maps. We used to do that all by hand. So I'm sure you've heard stories like this before. I call them back in the day stories. Okay, or back in the day, we did it another way. So I wanted to bring that out because it actually came up during a discussion at lunchtime today. So at any rate, back to the Kaparic River field, that young geologist finally convinced the senior management to go ahead, get out of my hair, go ahead and try this new method that you think is so good and see if it works. See if you can bring up the production any. That'll be the test, okay, if you can improve production. So that's what the geologist did. And now we see the answer. I've drawn it in for you. Okay, and what the geologist found was that these were actually a series of progradational sand bodies. Each one seaward, this was landward direction, seaward direction was out here. So there were prograding sand bodies like that, little downlapping planiform-like features. And they were not connected. They had shale breaks between them. The shale breaks. What was happening was that when another well would have been drilled, say another vertical well, you may have penetrated through shale breaks, or you may have stopped before you hit a shale break, and so you weren't getting all of the hydrocarbons out of these sand bodies. Well, the new guy came in and said, well, your correlation scheme that you've been using for 30 years is no good. You got to downlap these. Like that, like that, like that. And then let's see if we can't improve production by drilling a horizontal well. So that was another battle, drill a horizontal well. Because why do we need a horizontal well? We got all these wells in there, they're expensive to drill and all that. Well, they drilled the horizontal well, and that's what's shown in red. And that horizontal well crossed through every one of those shales, connected every one of those isolated sand bodies, and so drastically improved the production from that one well. And they did that, they ended up doing that in a lot of different wells, and it improved the production. So the senior manager retired, and the new guy became the senior geologist. Okay, so, but that's something that you face. Now, in this example, there was an added complication. Well, let me back up. What you're looking at up here now are maps of each of these individual sand bodies. Not only did the young geologist realize that you had a series of different sand bodies, but also realized that each sand body was a mappable unit, could be mapped by itself. The old maps that had been made just showed this as one sand, and it didn't show very much, not much change in thickness or anything like that. But when the new maps were drawn for each one of these sand bodies, each one of these sand bodies had a name. They gave them names. They called A1 was this sand body, A2 was that sand body, A3, A4, and then there was an A5 and A6. So at any one well, you might have seen something like this. And then you move to another well, and you may see the same configuration, but they might not be the same sands, because the sands are downlapping. And that was a mistake that was being made. So it was these shale breaks that really was controlling the well performance. And so, or affecting the well performance. So they drilled the horizontal all the way through, and throughout the field then they mapped. Here was A1, it occurred there. A2, here's the distribution of sand A2. A3 over here, A4, and A5. Okay, so what you're looking at, which way was land and which was the sea, for example? Here'd be land, here'd be sea, because these individual sand bodies are all prograding in the seaward direction. Okay? Now, there was one more complication that really caused a lot of problems, and that was the structure, because there's a lot of faults in this field, and the more realistic cross-section that was made is this one here. And what you see is a number of different colors here. Each color represents one of those sand bodies. For example, the black color down here represents sand number 1. The orange one here represents sand 2. The turquoise one represents sand 3. And purple one is sand 4. Green one is sand 5, so on. Notice what's happening here. So first of all, we put the structure in, and really complicated structure. So there's a fault, these are all faults. I can't draw a straight line, but those are all faults at any rate. I won't draw them all in, but that added another level of complexity. Now notice what's happening here. The black fault is pinching out right about here. The orange fault goes to here and it pinches out. The blue one goes to here and it pinches out. The purple one goes to here and it pinches out. The green one goes to here before pinching out. And so the fronts of each one of those prograding sands is dying out or pinching out further seaward, like you would get in a progradational sequence. Just the opposite, if we look at the back end of each one of these, let's just start here with this green. See, the green end starts right there. Well, I guess I can't really show this. Well, a little bit. I can show the green one starts here. The pink one is getting very thin over here. And the same thing with the green one up here. Actually, yeah, excuse me, the purple one. And then the green one is kind of pinching out right about there. So again, each one of these sand bodies is migrating seaward. And it was really a very difficult task to first, what the geophysicists had to do first was work out the structure, kind of reconstruct without all those small faults in there. They weren't really big faults either. But that was the first trick, was to do a reconstruction so you got rid of the faults, and then you could work out the stratigraphy. And this is a prettier picture of the same thing I showed you, where you've got progradation of these individual sand bodies. So each one of these sand bodies is deposited during a period of progradation. What do you think? When do you think the shales formed in between the sand bodies? Little period of marine transgression, depositing shale on top of the sand. Then progradation, little transgression, progradation, little transgression, and so on. So it was a understandable, geologically understandable reservoir, and which allowed an increase in the production. Here, this picture here just is another one that shows the distribution of those sand bodies. And once again, you're going from A1 down here to A4 here, and you're prograding in that direction. So one last point on this that I want to make is that what I said, the comment I made was that if you go to one well, you see maybe 4 or 5 sands. You go to the next well and you may see 4 or 5 sands, but they aren't necessarily connected. They aren't necessarily the same sands, and that's because of this progradation. So if we take, for example, let's take this well right here, for example. I'm going to use a light color. All right, here in this well, look at this well, you've got sand A3. You don't quite get to sand A4. A4 kind of pinches out just after that well, just seaward of that well. So you've got an A3 sand. You don't get into an A4 sand until you get to this well, and you don't get into an A5 sand until you get to that well. So In this well, you've got dominantly an A3 sand. In this well, you've got a lot of A3 and a little bit of A4. You get down to this well, for example, you don't have any A3 at all anymore. Okay, you've got some sands in that well, but basically they're different sands. And very important to know that then in terms of continuity of these sand bodies. So all of that more modern thinking, which is really, when we get into sequence stratigraphy, that's really what I'm talking about here. All that more modern thinking is has improved well performance in many examples. It's really kind of interesting as an aside, being a university professor, that this, I should probably save this for later, but I'll mention it now and then later again, that the concepts of sequence stratigraphy was founded, a geologic concept was founded in 1978. And a book was written on the subject in 1978, and it was revolutionary. Prior to that time, everybody thought, you know, your correlations go this way, they don't go this way, they don't go that way, and so on. So that kind of revolutionized, and not only that, but people have never really thought much about the effects of change in sea level and where that shoreline is. You never thought how that really affects the sedimentation patterns that you might get at one spot when you drill through a well. 1978, well, you go to some companies now, and they use this in their everyday work. They use these concepts in their everyday work. But so much to my surprise, after, let's see, 1978 to 2000 is 22 years, 38 years or so that this concept has been out there. And still, you'll go to a lot of companies that they just don't use it. You know, we never had that when I was in school. I guess I'm going back to my ideas now of the generation gap. But we didn't have anything like sequence stratigraphy. You just draw the, you know, you see the sands, you just draw them across without much thought to it. So some companies use these concepts. Those usually tend to be the companies with the younger employees, and other companies just don't use it at all. They do things the way they've always done them, and those companies normally aren't as successful. And that's because of the generation issue here again. Much to my surprise, being in a university where we'll take in graduate students that did an undergraduate degree somewhere, and a lot of the undergraduate students come in with no knowledge of the sequence stratigraphy. Can't believe it after 34 years, you know. And now all of our students, our undergraduates and grads, get a lot of it, and we use it in our day-to-day work on reservoir characterization. But I'm still amazed that after all these years, those concepts that have now evolved, and there's been so many positive test cases proving these concepts up, that still a lot of that don't use it. Some older professors, for example, might say, well, you know, I'm going to retire in 2 years. I don't need to learn some whole new concept, you know, something like that. So that's just a little side story. And if anybody ever tells another professor that I said it, I'll deny it. My colleague professors. Okay, so what we were looking at then, just going back to this little diagram here, what we were looking at was these little bottom set of beds. They're all prograding like that. So you drill your well across, so you cross cut those, so if you've got any shale, you cut right through the shale. Now, we didn't do a study up here, but the geology would be somewhat different. In other words, you wouldn't get these steep sort of cliniform features up here. They'd still be kind of gentle cliniforms, but not really steep ones on your, because these are your top set beds. This is higher energy though, deposited in a higher energy, shallower environment, and these down here are in a somewhat lower energy environment, and so we can say that these sands, lower energy, they're progradational sands with lower energy, but they're not going to have as good a reservoir quality, and they're going to be stacked. They're going to be stacked and prograding. These sands will tend to be more aggrading, okay, vertically, and they'll have better reservoir quality because they were deposited in a more energetic type of environment. So these are subtleties, but one thing you should never do, that I just never like to see, when someone says, something here. When somebody says, okay, I got some sands here, I got some sands there, they're just sands, you know, they're all the same sands. Hopefully I've convinced you now that they're not all the same. We haven't gone through the exercise here, but what you would find is that these are more top set type beds, whereas these are more the bottom set, and then the slope shales are in between. And so never take it for granted. Another thing that I'll just point out to you all is that again, you should never say or take it for granted that your sands have the same reservoir properties. And that includes, for example, I just showed you the study we did on this lower sand. One thing I should never, and if we had not done a study of the upper sand, I could say, well, it's all sand, you know, so the characteristics of this lower sand are going to be the same as the characteristics of the upper sand. So I can save some time now. I don't have to do a reservoir characterization of the upper sand because I did it for the lower sand, and it's all just sand. So don't make those mistakes, okay? Because that rarely is that true. Usually there are differences in these sand bodies, and it all goes back to the way they were deposited. Well, why don't we take a break and for a few minutes, and I'll carry on from there.
Uy, pásame la foto. Y Google Earth no puede. Sí. ¿Te lo utilizas? Ah, ya.
Marcelo. Ya. Aquí está el carbono superior, este es el actual. Océano, oligoceno.
Mira cómo se va
eoceno.
entrando el océano.
Sí.
En realidad va retrocediendo el océano.
Ahí miren el océano.
¿Cuál es el Triásico?
Tiene
El Cretácico está. Ya se llevó hasta Cochabamba, el océano.
Ay, te como Livia, qué bonito.
Y es muy bueno, ¿eh?
Cretácico.
Será
Jurásico.
añadida a
Ah, está
la
bonito.
simulación.
Jurásico.
Está unido.
Ve, mira,
Está
mira,
unido.
está unido.
¿Cómo, cómo?
Bien.
¿Lo descargaste, Carlos?
No, un docente en la universidad nos dio esta clase
Ah, bien.
y nos,
Pasa
y
nada
nos
más.
pasó esto.
¿Es pesado o lo puedes mandar
Es
por...?
un PowerPoint, les paso a todos.
Ah, entonces mándalo por mail si no es pesado.
Ya.
Imágenes.
Ya.
Cuando estamos
¿Y
abajo
cuál es el que
de
inicia de Cochabamba?
Mira el
Mira,
carbonito, mira mi hermano.
mira, todo inundado.
sí,
Por eso el carbonífero de pelo. Carbonífero y de Devónico. Devónico igual.
Igual.
Justamente.
Y latitud polar, ¿no?
sí.
Eso también es glaciar marino, entonces, frente al ambiente.
El silúrico, ya Bolivia,
Totalmente.
ordovícico,
Pero es somero, ¿no?
ordovícico,
Claro.
medio, el cámbrico,
Precámbrico.
el cámbrico.
Debería ser al revés, pero. Ir desde el precámbrico.
Claro, debería ser eso, porque al final está
Claro,
el actual.
la actual.
Cuando está arriba el actual, aquí está el actual.
Oye, muy buena. ¿Cómo se llamaba tu profe?
Neomesio Choc.
Por favor, como me lo pasen por correo con su nombre para que le ponga los créditos. Yo lo voy a utilizar.
Debe estar su nombre tal vez aquí.
Ah, ahí está, pues.
Ahí
Aquí
está
está,
bien, Neomesio Choc.
Es que él trabajaba en el Sergio Min, en el Sergio Tecmin.
Y tienen el señor
Y nos
Muy
pasó
bueno.
esto. Sí.
Eso ayuda harto para ver los paleoambientes dominados.
Claro, en esa época. Es que Este de acá, el que me decías del dorado,
Ajá.
este que nos está explicando más se parece.
Más se parece, ¿no?
Ajá, más que el delta.
Más que el...
Porque justamente
que el
coincide
Size
en
Valley.
en que Guanaco tiene mejores propiedades petrofísicas que la Mora. Las dos son cadenas y son de los espesores relativamente
Habría que ver los
delgados.
registros si muestran ese comportamiento de gamma ray.
Sí, porque interesante es que las propiedades petrofísicas de la arena superior siempre son más
Claro.
y son arenas delgadas, porque si te estabas fijando en el llano que nos mostró, ¿no? Son arenas delgadas.
Claro.
Bonito.
También eso sería bueno para verlo con los resultados de Colorado Sur.
Está
Con
bueno.
Dorado Sur ya puede explicar que es una zona de clinotero. Ahí está.
Habría que bueno, tratar de... Sería bueno, vamos a ver si se ve algo del comportamiento actual, si sí me cae algo bonito, pero ya después la...
Clarito.
Clarito. Qué bonito, ¿verdad? Y lo bonito que te pone a Bolivia ahí.
Sí, sí, lo mejor porque sepan dónde estamos.
Claro.
Cada vez más separados.
Sí.
O los cenos más recientes.
Sí, el último, es el océano. No, y el océano.
Ese es aparte, no es igual.
Pero eso está mal. No debe ser paleogeografía actual, debe ser geografía actual. ¿No?
Exactamente, ¿no? También estamos que estudian lo que va a pasar en el futuro, ¿no?
Se hacen simulaciones. Mira ahí. Empieza. Mete más. Muy buena, ¿verdad?
Ya
Ahí
se
en el
pegó.
Cretácico estaban unidos.
Pegado.
Probablemente estaba bien. Probablemente era el frío.
Pegado. Igual eso fue muy bueno lo que hace un reportaje, cómo descubrieron que anteriormente estaban unidos este bosque.
Por los fósiles que se han encontrado.
Encontraron un dinosaurio que era el mismo en ambos lados. ¿Cómo puede ser que están tan distantes por el mar y sea el mismo?
Porque era
La mitad un dinosaurio, ¿no?
El
Que
mismo
somos
de agua.
No, sí,
Les paso entonces.
Ya,
Gracias,
nos pasamos.
Estamos abajo.
Súper
Sí,
fácil.
es muy pesado lo que es.
Sí. Está Jorge.
Roger Slatt. I'm returning Dave's call. All right. Okay. Okay. Yeah, how you doing? Okay, doing well. I hear you're having a heat wave up there in Denver. Oh, okay. All right. Yeah, let's see, you called, didn't you? Hello? Yeah. Yeah. Can you hear me? Okay. Yeah, you called me a while ago, didn't you? Yeah. Oh, yeah. Okay, yeah. Right. Yeah. Okay. Okay. Oh, okay. I thought you just phoned a few minutes ago. No? Oh, okay. All right. Well, my mistake then. So, okay. Well, that sounds good. Butt call. Okay, good enough. Well, yeah. All right. Bye-bye.
Funciona para eso, ¿no? A ver, levanta. Si funciona, ¿no? No creo, ¿no?
No.
No pasa.